Hi everyone, I'm Zhang from Chicago. Today I will talk about the internet video streaming. Actually, improving the quality of experience, as known as QoE of video streaming, is not a new topic. In this talk, I will show the missing opportunities in improving QoE. In the past years, although the network bandwidth has been expanded a lot, bandwidth is still not enough to provide desirable QoE to every user. Especially during the COVID-19 lockdown, the content providers lowered their default video resolution to relieve the internet traffic pressure. So our goal is to use smaller bandwidth to achieve similar QoE as before. To improve QoE, the conventional wisdom selects bitrate for video chunks according to network throughput, and they trade the video chunks equally. It is because of an implicit assumption that user cares about quality in the same way throughout a video. So video quality should be optimized using the same standard everywhere in this video. However, we argue that the users have different sensitivity to the quality of the chunks. In the following slides, I will show two videos. The two videos are with the same content and with a 1-second rebuffering event, but the rebuffering happens at different places. So, from the conventional perspective, these two videos have the same video quality. Let us watch the two videos now and keep a question in mind. Which video do you think have better video quality? This is video A. This is video B. Now, go back to the question. Which video do you think have better quality? I guess most of you will select video A, because we really want to know whether this shot leads to a goal. This soccer video has two parts. For video A, its rebuffering event happens as the normal playtime. To get the QoE of video A, we recruited real human beings to read video A, and we normalized their ratings to the range from 0 to 1. Their average rating is 0.73. We did the same thing to video B. The average rating is 0.42, which is much lower than A, because B's rebuffering event happens in a more critical part than A. We can see that the users have different tolerance to rebuffing. The fundamental reason of such a discrepancy in the ratings is that the user's sensitivity to video quality varies with video content. We speculate that the difference in quality sensitivity comes from users paying different degrees of attention to different parts of the video. For example, for video content, if a user is interested in its content, it is natural that the user expects to watch this chunk in a high quality. To put this insight into video streaming systems, we need to answer these three questions. First, whether the variability is large enough to let us optimize video streaming. Second, how do we quantify the quality sensitivity? The third is how to leverage it to improve adaptive video streaming. To demonstrate the variability, we do a simple experiment. We add a 1-second rebuffering event at different places in the source video. We ask the crowd workers to read those videos, and then we measure the variability of their ratings. For a source video, we define the QoE drop delta at time t to indicate the quality sensitivity of the content at time t. The variability is defined as the maximum difference of the QoE drop at different time. In this figure, the x-axis is the variability of 16 source videos in our dataset. We can see that for around 50% source videos, the QE drop varies more than 110%. So the users have large variability of the tolerance to rebuffing. It gives us an opportunity. We can lower the video quality when sensitivity is low for saving bandwidth for the nearby chunks whose sensitivity is high. Now, let us integrate the quality sensitivity into the existing QE models. In the traditional QE models, the QE of a whole video is usually predicted as a sum of the QE estimates of individual chunks. In SENSEI, we reweight those chunks by their quality sensitivity. Here, we are not going to retrain a new QE model for the source video, but just to add a parameter to the existing models. An immediate question comes up: how to capture content-dependent quality sensitivity? A straightforward solution is to use video sentencing models. For example, for the motion-based model, AMVM, the chunk sensitivity is modeled by the magnitude of its motion vector. And for some other models, like DSN and videoto, they evaluate each chunk's intrinsics. However, those models do not work very well. Let me explain it by an example. Remind the soccer video we just watched. In the user study, the normal play time is regarded as an insensitive part, while the goal is sensitive. But those sentencing models give us the opposite results. Intuitively, the wrong prediction is a misalignment of the sentencing model's purposes with the quality sensitivity we want. Now, how about we directly ask crowd workers about quality sensitivity? It has a lot of pros. First, we can directly link video quality to QE. Second, it is worth paying the cost for popular on-demand videos, considering that the video content providers spend billions of US dollars every year to make video content. For the cons, it might be a concern that the cost is high if we evaluate the quality sensitivity for every chunk and every type of low-quality event. Also, the responses might be not reliable, which makes the QE model not accurate. Last, it is not able to deal with live video streaming due to the strict latency requirements. To reduce the crowdsourcing cost, we need to let the crowd workers to rate fewer videos. Our idea is to use coerced quality sensitivity. It means that we can group the chunks that might have similar quality sensitivity. Then we zoom in one representative chunk in each group. We can do more surveys for refining the weights. We developed a method called two-step scheduling to implement this idea. In step 1, we identify the chunks that share the weights. In this example video with 3 chunks, we add a 1-second rebuffering event to every chunk separately. If the user's ratings are similar when the rebuffering event happens at some chunks, those chunks could share the same weights. In this example, we assume 2 and 3 share the same weights. Then, in step 2, we only focus on the representative chunks 1 and 2 to refine the weights at different quality levels. The other challenge is unreliable responses, because the workers might provide random responses for completing the task as soon as possible. To control response quality, we follow the common practice from previous literature, but tweak a lot for our case. More details can be found in our paper. By these quality control schemes, we use reliable responses to train QE model with high accuracy. Now, let's put all the things together in the ABR algorithm. Compared with the traditional ABR algorithms, what's new in SENSEI is SENSEI can lower the quality of insensitive chunks to achieve high quality for sensitive chunks. Let's look at an example. In the traditional ABR logic, they do not distinguish the chunks by their quality sensitivity. So the rebuffering event only happens when the buffer drains out. Let's review the video content when the rebuffering happens. It is at the sensitive chunk, so the QE will be affected a lot. But in SENSEI, if we know there is a sensitive chunk nearby, even if the buffer is not empty, SENSEI could still invoke a rebuffering event. and use this time to download sensitive chunks with better quality. Here is an experimental setup to evaluate SENSEI's performance. We run SENSEI under videos and network traces from open source dataset. We compare SENSEI with recent ABR algorithm, Fugu and Pensive, machine learning-based ABR algorithms, and BBA, a buffer-based ABR algorithm. We compare SENSEI's QoE with other algorithms under the same bandwidth. In this figure, the x-axis is the QoE gain over BBA. We first show Pensive. Each point on the line represents the gain over BBA under a network trace and a source video. Then we show the performance of Fugu and SENSEI. We can see that SENSEI has 15.1% higher QoE on average. We also evaluate QoE bandwidth trade-off of SENSEI. When the throughput varies, SENSEI constantly gives better QoE than other ABR algorithms. On average, SENSEI have 26.8% less bandwidth usage, but the same QoE as other ABR algorithms. Now, we look at how the crowdsourcing costs affect QoE. The cost-saving techniques can save 30 times the cost, and the cost is only $31.4 per minute video. Due to the time limit, we put more details in our paper, including the accuracy of SENSEI's QoE model, the number of workers we need, and the parameter selection for the user study. In the end, let me summarize this talk. First, our observation is that for viewers, different parts of video have different quality sensitivity. Second, our key idea is to embrace the variability of quality sensitivity to improve QoE by crowdsourcing. Third, SENSEI improved video QoE by 15.1% or save bandwidth by 26.8% on average with a cost of $31.4 per minute video.